It really is a pleasure to be here today to welcome, to help to inaugurate this series in honor of Jim Arnold and to be able to contribute in some small way, because I share the kind of respect that all of you people feel for Jim. Jim has been a leader in everything he's done in developing his own field of radiochemistry and cosmochemistry here at UC San Diego. People have looked in this direction for an awfully long time. As Dean Mark Thiemens just said, Jim's work in founding the chemistry department set a mark which the rest of us have been very, very eager to watch for a long time. What he did in creating the California Space Institute and in allowing many other people to think about the Earth's place in the cosmos and the solar system, and to think about questions of habitability, not just the mining of asteroids and so forth, but questions of habitability of other objects, and of course the Earth. We owe Jim a great deal for these thoughts and questions which encourage the rest of us to begin to ask. So it's a great pleasure to be here. What I'm going to do today is to talk about the Earth's changing climate in the context of an unusual situation that occurred a year ago when the White House asked a series of questions of the National Academy of Sciences and asked the Academy to respond and to do it very quickly, because the President was preparing for a series of trips to Europe and elsewhere, and also wanted to try to figure out what to do about some international agreements that the U.S. had already signed, but the new administration wanted to rethink. Well, the request to the Academy was an unusual one, in that the Academy, as many of you know who have helped on these NRC and Academy reports, the Academy usually takes a year, 18 months, 2 years, sometimes longer, to do reports. So the White House warned the Academy powers that be that this report was needed more quickly. And when Bruce Alberts and staff asked how quickly, thinking maybe 6 or 9 months, the answer came back 4 weeks. So Bruce had to think whether that was a suitable situation, but eventually Bruce and the other officers of the Academy and the NRC decided that when the President, especially a new President, asks the Academy to respond, the Academy really had to try. So Bruce asked me if I would chair the group, but he also asked whether I thought it was possible. And I agreed with him that we didn't know what kind of a report we could assemble in just 3 weeks by that time, 3.5 weeks, but we agreed to try. Now what I'm going to do is to show you the questions that the White House addressed to the Academy, and we tried to frame our answer, our entire report, in response specifically to those questions, and to try not to stray at all into political statements or out of the realm that would be required to answer the questions. For example, we did not talk very much about the biology of climate change, either in terms of causes or impacts, but only insofar as we would have to answer the questions. Well, before I launch into the questions of that report, I'll talk for just a few minutes to give a little bit of background on Earth's climate and this very question of why it is that anybody thinks that humans are capable of causing a change to the planetary climate. And it has to do with the Earth's energy budget. Then after that, I'll launch into the questions that the White House sent and choose a few of those just to give an example of the kinds of reasoning we went through. The context, of course, is important, and I'll get to that also. But if I may have the first slide. I think I can do that from here. There will be many slides in today's presentation which originate from people here at UC San Diego or La Jolla. It wasn't easy for me to, it wasn't at all difficult for me to arrange that, because so much of the best work on climate science has taken place here. This is a schematic, obviously a cartoon image of the Earth with terrestrial and oceanic surface on it. The numbers in boxes are in the units of watts per square meter. And for example, 342 represents the annual day-night average of sunlight incident on the Earth at what we might call the top of the atmosphere, 342 watts per square meter. The 105 represents the 105 watts per square meter, which on average, day and night, winter, summer, 12 months a year, are reflected directly back to space from the tops of white surfaces, such as clouds or other white surfaces at the planet's surface, such as snow and ice. 237 then, by difference, represents the steady state rate of energy absorption, its power, rate of energy absorption per square meter. And to a first approximation, this is the planetary energy budget, to a very good first approximation. Visible and infrared light coming in from the sun, 1% or so of ultraviolet light, with about 1/3 reflected back to space, and 237 watts per square meter absorbed. So, if we were trying to invent a way for humans to change the Earth's climate, for example, by warming it, I'll start with an obvious suggestion which sometimes people make to me when I speak publicly, that perhaps it's just by our burning of fuels. Well, this is just a quick summary of how much burning of fuels is taking place. I think I can focus that a little bit better. The entire human usage of energy, I'll try to get this focused, planetary-wide in the mid-90s was units, whatever you are familiar with, 3 times 10 to the 20 joules, or about 10 to the 14 kilowatt hours annually. That's the entire human energy usage by the burning of oil, gas, coal, wood, nuclear reactors, solar-powered systems, wind and geothermal energy which is captured. Now, if you work that out according to the population worldwide, that turns out to be about 2 kilowatts average power consumption per person worldwide. And if you convert that into the units I just used, it's only 0.02 watts per square meter, because after all of our energy usage is eventually dissipated into waste heat, which then, if you average over the planetary surface, is only, as you can see, 1/10,000th of the energy incident from the sun, 237 watts per square meter absorbed by the Earth, atmosphere, planet system. But all of the energy used by humans is 1/10,000th of that, spread out over the planet. So you get the feeling that we could increase our rate of energy burning and usage quite a bit before we would come anywhere close to impacting the total planetary energy balance because of the sun's numbers that I just gave you. Now, in the US, we're rather more extravagant in our usage of energy per person, so that the average energy usage is more like 10 kilowatts per person. The spatial intensity is about 1/10 of a watt per square meter, 5 times larger, but it still falls far short of the incident light and energy coming in from the sun. So the bottom line is that trying to change the climate by burning more fuel will not work, at least not for the foreseeable future. The first time I did this calculation, the ratio was 1 out of 12,000. Around 1970, the ratio is now 1 to 9,000, so we're catching up on the sun, but we still have a long way to go. So how is it then that we can speak about humans being capable of affecting the Earth's climate? And the answer, of course, is the greenhouse effect. And we have 2 ways to illustrate that the greenhouse effect does operate on the planet, has been operating for a long time, and is basically keeping the planet above freezing. This is just some scratchings, knowing that many people in the audience are scientists. I have a few numbers. The steady state energy balance of the Earth is represented by the 342 multiplied by 4. This is the energy density per unit time striking the Earth's out at the outer atmosphere. The 4 is just a bit of geometry, but the point is we can calculate the temperature of the Earth, an effective temperature of the Earth, by using the incoming energy from the sun, multiplying by the fraction that is absorbed, that is 1 minus the amount that's reflected, and in steady state making this equal to the radiation which must be emitted from the planet in a Planck's black body emission. We can calculate from this equation what the effective temperature of the Earth is. We know this value within about 0.5%. We know the reflectivity of the planet within 1 or 2% on average. We know the Stefan-Boltzmann equation, so we can simply calculate, of course assuming there's no time variation, And we know that the temperature of the planet is not changing very rapidly, so this is not a bad approximation. And lo and behold, we calculate that the temperature of the Earth is minus 18 degrees centigrade, below freezing, or 255 Kelvin. Something is wrong. If you do the same calculation for Mars, as many of you know, with the thin atmosphere of Mars, you calculate the temperature of Mars exactly. If you try, it's perfect. If you try to calculate the temperature of the planet Venus, though, you also underestimate the temperature of the surface of the planet by a great deal. The answer is indeed the greenhouse effect, and I'll now talk about that just a little bit. That is, what is missing in the calculation? It is the presence of an atmosphere which interacts with the planetary radiation in such a way as to keep the surface warmer than it would be otherwise. And also the presence of liquid cloud material is missing in that calculation. I'll go ahead then to show one other piece of evidence for the existence of the greenhouse effect. This graph is from one of the first instruments that flew around the Earth that was for scientific purpose. It was an infrared emission measurement, IRIS. And the dashed curves, which are smoothed curves as a function of wave number, and of course this is just the inverse of wavelength. So this wavelength would be 10 microns, 8 microns, 7 microns, 12, 15, and so forth. If the satellite instrument had observed the smooth curves with the temperature shown when it looked down over the Mediterranean, we would have been seeing just the emission from an idealized black body. Instead, the actual data are anything, not quite a smooth curve. In some regions, they fit the temperature very well. So in this region, wavelengths, the system looks like the temperature of the surface of the Mediterranean then, about 283 Kelvin, or about 15 centigrade. Here, though, clearly there's something different. Then the curve resumes its shape that matches the temperature of the surface of the Mediterranean. And here, in the wavelengths where carbon dioxide is very active, the temperature effective seen by the satellite was only 220 degrees centigrade. In a way, this demonstrates the existence of the greenhouse effect on the planet, because what the satellite is seeing is not all the way to the surface of the Earth. In those wavelengths where the atmosphere is transparent, such as here, the emission, that is, the satellite can see all the way to the surface of the Earth and indeed detects the surface temperature of the Mediterranean. Whereas in this wavelength region, which happens to be an important one for absorption by ozone molecules, the satellite can only see into the ozone layer, say 25 kilometers above the surface, because the radiation that's leaving the planet's surface at this wavelength, which if there were no ozone, this curve then would have been smooth and clear through here. Instead, the presence of ozone as a greenhouse gas interrupts the flow of energy to space, and in this way, it's actually much more complicated than this, keeps the planet warmer. Well, that's the context. What I'm going to do now then is, because of the reality of the greenhouse effect and because of some early calculations and observations that certain chemicals in the atmosphere are increasing worldwide, there has been growing concern, certainly since Ravel and Seuss's paper in the 50s. There's been a great deal more concern over the years as numbers have become more clear that the human impact of changing the chemical composition of the atmosphere may indeed lead to observable climate change in our lifetimes and a growing climate change as time passes. One of the early calculations is summarized here that Bob Dickinson and I did in the mid-'80s, where we simply looked at data on how much carbon dioxide had changed from its pre-industrial concentration of 275 parts per million, of course measured by Keeling et al., to its 1985 concentration, and we calculated then in the same energy terms that I've mentioned earlier how much extra energy is being trapped near the surface of the Earth because of that composition change of the increase in carbon dioxide, and similarly for some of the other leading greenhouse gases. And we calculated by the mid-'80s that the change in the Earth's energy budget at the surface was already over 2 watts per square meter. So 100 times larger than the impact of burning all of our fuels, but still 100 times smaller than the total solar input. But in geological timescales, to do something in a period of just 50 years that changes the entire planetary energy budget by 1% is rather dramatic. And many more calculations over the years and many more observations have, and now large-scale climate models and other climate observations have added to the concern, so that by 1992 there was a framework convention signed by most of the nations of the world in Rio de Janeiro, including the United States. And I'm going to use a phrase now that will come back, and you'll see it in the White House questions. In 1992, the Framework Convention to Prevent and on Climate Change committed the nations of the world to preventing the accumulation of dangerous amounts of greenhouse gases in the atmosphere. And the former President Bush signed on to the convention. Then in 1997, after several more meetings, many nations of the world agreed on a so-called Kyoto Protocol, which took certain steps towards binding obligations of various nations to limit their greenhouse gas emissions. And of course, this treaty, this protocol, has been much more contentious and starts to involve some detailed actions on the part of nations. And in late summer, mid-summer 2001, the current President Bush decided to pull the United States back from that protocol and to not commit to it. So in the year 2001 then, these are the questions that came over from the White House to the National Academy of Sciences, and I'll read several of them to you and focus on several. And we were asked to provide answers to these questions in a period of about 3 or 4 weeks. And as we did this, we learned much more about the context of what was going on in the new administration. It was extremely surprising for us to find out how much work was going on inside the White House. Fairly high-level staff people, middle-level and policy people had been working full-time, virtually full-time on climate change for a period of 3 months. Some of you were probably invited to some of the meetings that they were having, private meetings in the White House, to try to prepare the new administration for making its decision. We found out that the cabinet had been working very hard, and so these questions were coming in from various sides of the White House and the climate. The first question is indeed a quite valid one. What is the range of natural variability in climate? And I want to give just a few picture slides about that. Then several questions about greenhouse gases and human activity leading to emissions of greenhouse gases and how sure we are of this information. Then a few technical questions about basically reversibility. What can be done, or how long does it take nature to cleanse itself of the greenhouse gases in the atmosphere once they're put there? And at the bottom, a question, is climate change occurring, and if so, how? And so forth. I'll focus on the first question first. What is the range of natural variability in climate? We did give eventually a specific answer, but just for the fun of it, this slide is not visible as it is, unfortunately. But it's, I don't know if the lights can be handled or not, but it's a rendition from a standard geology textbook showing an attempt to reconstruct the glacial cover over North America. And this one happens to be 7,000 years ago. The outlines of North America, you really cannot see it here, but North America basically covers the slide. The Great Lakes region is up here, and by one reconstruction, there was that much glacial cover over North America 7,000 years ago. This was a reconstruction of 9,000 years ago, 12,000 years ago, and at the height of the last ice age, showing the extent of glacial cover over North America. The point is, there is all kinds of evidence of previous climate changes, remnants of glaciers, certain topographical features, biological debris, and so forth. There's a slide that I do want to show that, while we have the lights down, This is of an inland glacier in South America that many of you can identify. But those of you with keen eyes can also see annual layers, where the glacier has annual layers that are formed by the new precipitation, snow, and then compacting into ice, the closure of the firn, creating a stratigraphic record of time that can actually be counted year by year. And this glacier is particularly difficult to work on scientifically because it's so exposed, but the fact that it is so exposed allows us to see the annual layers deposited. So the reason I show this glacier is that along with evidence of past climate changes and differences, glaciers can also be cored. And this is a photograph from a laboratory in Bern where scientists are removing a cylindrical core that had just been extracted from a glacier. And now by slicing that glacier and crushing it and extracting gases and particles of various kinds and even some radioactivity, can determine something about past climate change. In particular, the previous amounts of greenhouse gases that were in the air in certain periods of time back. So in this report, we talked a little bit about past climate change and certainly stated that the Earth's climate is probably always changing. It's just a question of how rapidly and how deeply, and of course of our understanding of the causes. And there are no perfect explanations of these changes and probably never will be. But while I am mentioning ice cores, I want to show some smooth data that go over the the period since the Industrial Revolution, namely from about 1850 to the present here, showing ice core records of carbon dioxide, methane, nitrous oxide, three prominent greenhouse gases that also have natural sources besides human-caused ones, and then also chlorofluorocarbons, which are potent greenhouse gases, but which were only introduced into the environment synthetically by humans beginning about 1950. The point of this is that these ice cores, a relic of past climates, allows us now to reconstruct something about the composition of the atmosphere, which then leads into some of the other questions that the White House people asked us. So these kinds of records show, for example, that carbon dioxide, at least over the past 400,000 years for which ice cores have been used now, carbon dioxide amounts have never been as high as they are in the modern era of the last 50 or 100 years. And I'll show more data like this later on. Let's see where I am here. I have one graph that I want to show you from here from San Diego, that a recent compilation that Dave Keeling has put together that makes the point more clearly. This is a record of atmospheric carbon dioxide over the industrial era. So I was just showing the period of time from about 1850 to the present, where each of these points now represents the average of a number of ice core extractions, showing that back into the 18th century, carbon dioxide amounts were bounded around 280 parts per million. And then when the era of fossil fuel burning started and has accelerated, so that these last 45 years of data are in fact Dave Keeling's actual measurements, we see the trajectory on which we are. Now there is no record in the ice core of any amount of carbon dioxide larger than about 285 or 290 parts per million. Perhaps back in the Carboniferous age, millions of years ago, there was more carbon dioxide, but the only direct measurements we have of carbon dioxide amounts before large human changes were introduced is that carbon dioxide varied between about 180 parts per million and 280 parts per million. When the climate was cold, there was usually much smaller amounts of carbon dioxide. In interglacial periods, the natural carbon dioxide amounts were about here. I'd like to show one more transparency while I have this machine on, And that then gets to the other question of natural climate change. This is a record of actual temperature measurements in the last 120 years from meteorological observations, where care has been taken to delete observations made from cities, where we have an obvious warming introduced by cities. And what it shows is a fair amount of variability, where 0 is the baseline or average of the whole data set. It's not 0 degrees temperature, but instead this is just the temperature difference from average. We believe that this kind of temperature record does include some kind of natural variability. And there's a great deal of research going on underway now around the world on a yearly time, to try to understand on a yearly time scale, a 10-year, a decadal time scale, as well as a century time scale, the kinds of physical processes that could give rise to this kind of variability of temperature. You'll see, and I'll talk about this more later, that this may be the rebound from what was called the Little Ice Age of the 15th and 16th century. That is a natural warming, although there's perhaps more dispute over that statement now than there was 5 years ago. 5 years ago, I think there was a fair consensus that this warming perhaps was a rebound from the Little Ice Age. Now I think there's more disagreement. The climate did warm from about 1900 to 1940, fairly steadily. Then there was a slight cooling from 1940 to 1975, and then a rapid warming in the last 20 years, and we will return to that. So there are all kinds of thoughts and ideas and investigations underway to try to understand this record in terms of natural variability, looking at the record of volcanic eruptions, leaving debris behind in the atmosphere, which then reflects sunlight back to space, which cools the planet, and so forth. And probably most richly, the exchange of heat between air and oceans and natural cycles therein might give rise to some of the shorter term variations, but it's possible long term also. I'll return to the slides then and get back to these questions. Probably the part of the picture that's understood the best, where we could be as direct as possible in our replies to the White House, were the greenhouse gas types of information. The questions were certainly fair, but as it went, these were probably the most direct answers we could give of all the questions that were asked. Because with carbon dioxide, there is a great deal of understanding of the actual amounts in the air, the way they change from point to point and with season. And then, of course, we want to explain why. This is a record of fossil fuel CO2 emissions since essentially the Industrial Revolution, or when it really took seat in 1850, showing annualized growth rates of nearly 5% per year in worldwide carbon dioxide emissions. These are measured in terms of carbon here, so that current emissions of carbon dioxide as carbon are about 6 billion tons per year worldwide. And you'll see that the growth rate of those emissions, though, has changed with time, and there are annual fluctuations such as occurred during the Second World War, after the oil shocks of 1973 and 1979, when there was temporary strong commitment to energy conservation and some technological innovation leading to more energy efficiency. But the general picture is one of upward trajectory in the combined fossil fuel CO2 emissions, so that the current understanding of the carbon dioxide increase is something like this, that it is caused perhaps 75 or 80% due to fossil fuel emissions. Now, the year-to-year record is more peripatetic, a little bit less easy to explain, but certainly averaged over a decade or 20 years, 75 or 80% of the carbon dioxide emission observed in the air is due to the fossil fuel emissions. There is isotope evidence and some very quantitative calculations to back this statement up. The other 20 or 25% of the carbon dioxide increase that we've seen in this century is due to the clearing of land, largely in the tropics, partly due to the burning of old wood and old vegetation, but also partly due to the subsequent loss of organic matter from the newly exposed soil, much of which soil is used for agricultural purposes immediately. So that's the balance. About 3/4 or 80% due to fossil fuel emissions as a cause of CO2 increase, and 1/4 or perhaps 20% caused by land clearing, especially in the tropics. I want to mention methane because it's not only the #2 greenhouse gas, but one of the key observations in allowing us to construct a budget of methane and try to figure out why it is increasing in the worldwide atmosphere is due to radiocarbon, a subject to which Jim has contributed so much. Some key observations of the carbon-14 in methane made before atmospheric bomb testing had completely wiped out and messed up the Earth's the budget in the late 50s and early 60s showed that the methane present in the atmosphere was well over 90% biogenic. That is, the carbon in the methane extracted from the air had recently been in something living. The methane probably being produced microbiologically. This observation continues to hold. It's much more difficult to make these measurements now because the carbon-14 in the air, there's still some residual bomb carbon-14, but worse yet, there's carbon-14 methane in the air from pressurized water reactor, nuclear reactors, so that now it's not at all easy to do this kind of measurement anymore. But the reason I mention the measurement is it created a very solid constraint to anybody's theorizing about where the methane is coming from. So we began doing research on methane while I was here at Scripps, making measurements of the methane emission from rice paddies and from animals, where these are simply chambers put in place in a rice field in Northern California. I thought that rice was grown in Southern California when I started this measurement, and I didn't know that it wasn't. But we really wanted to do these measurements so badly that we went to Northern California. This very green patch is a section of the rice paddy that was given extra nitrogen fertilizer. The more yellow patch there was treated more wildly. But the point is, it was the carbon-14 that gave the clue that most of the methane sources must be of biologic origin, that allowed a number of people, this has become a cottage industry around the world now, to try to figure out where all the carbon dioxide and methane and nitrous oxide is coming from. This is one budget where, that I'm proud to say it has withstood the test of time. No one else has ever used this notation, but I did it because of my absolute conviction that carbon-14 was the way to look at this problem, Jim. This HEDC means hypothesized equivalent dead carbon. And it allowed me to, along with Ron Oremland, to put together a budget of atmospheric methane sources, adding up to 500 million metric tons a year with a breakdown like this. And the constraint, we had several good constraints that made these numbers at least add up to the right total. This constraint comes out of carbon-14. We can only have 1/5 or less of the total sources being radiocarbon free. Otherwise, we violate a serious constraint. And since then, many people have tried to calculate methane budgets. They don't understand carbon-14, and they get it wrong. So thank you, Jim, for at least allowing me to avoid that mistake. So if people want to say that coal mining and natural gas drilling and venting or large burps of geochemical methane are entering the air every year, they have a real problem because they can only hypothesize that dead carbon methane can reach that number and no larger. So that helped a lot. With the methane budget, though, getting back to the White House questions, we do have pretty solid evidence that about 2/3 of the methane sources, the red part of the pie chart, are due to human influence, not necessarily human control, but activities that are under human management, not necessarily controllable. Whereas the yellow part represents natural methane sources that have probably been in place for a long time, including some not at all well-known source of methane being released from the world's open oceans and some coastal regions. The individual numbers here are very, very difficult to get right. The correct number for rice paddies, if we know it, is probably less than that. The correct number for ruminant animals, enteric fermentation, 80 teragrams methane per year, is probably a little larger than that number. This work was done in 1988, but the budget has hung together very well. And when we really must answer business people and government leaders how much we know, I think we can say safely that the increase in methane worldwide is almost entirely due to human activities. Now, getting back to energy, what does all this mean? Are greenhouse gases really causing the climate change, and how much of the change, if it could be due to human activities? This now gets back to the same kind of units I had mentioned earlier, watts per square meter. So adding up the forcing, that is the greenhouse forcing beyond the natural greenhouse effect, that is due to the increase in the greenhouse gas concentrations of CO2, methane, and so forth, we now have a figure of about 2.3 watts per meter squared, so the number is slowly growing. This is a consensus kind of a calculation that a number of scientists have contributed to. As we move further to the right, the numbers become less certain because the measurements are more difficult to make, the calculations are more difficult. So for example, ozone in the lower atmosphere, the fact that it has increased somewhat is giving us a warming, whereas the observed ozone loss in the stratosphere is giving us a global cooling. I'll mention just one other. Volcanic aerosols probably have caused a net cooling over the last couple of decades, but volcanoes have their own time schedule. They erupt more or less randomly, so this number has a very different characteristic to it than greenhouse gases, which may reside in the atmosphere 100, 200 years, as opposed to some of these other shorter-lived entities. The point is, though, we are trying to make stronger and stronger connections between the perturbations to the global energy budget, 2 watts per square meter, with the human factors that are causing the atmospheric and oceanic and surface changes that lead to the forcing. This is a similar graph, but with a confidence scale on it, whereas the greenhouse gases and their numerical change to the global surface budget is estimated with very high confidence. As I said, the ozone amounts with perhaps medium confidence. It's been hypothesized that the sun is releasing more energy. On this sketch, I said low confidence, and later on I'm going to make it even lower. We have some very potentially large impacts due to changing Earth's aerosol content, and there are certainly leaders here at UC San Diego working on that issue. And land use change itself can be causing a forcing, but we have very low confidence in those figures at present. So you remember the old joke about a scientist testifying in Congress, and after talking about this and then on the other hand that, the senator who was convening the hearing said, "I really wish for a one-armed scientist." Because we really do a lot of this on the one hand, on the other hand. So in writing this report, we tried to say what we could as directly as possible and then to indicate all of the uncertainties, obviously very honestly. To continue along these questions, this is now the second sheet of the questions. There were a total of 13 or 14. And I've just been touching on our greenhouse gases causing climate change. Well, we can certainly say that they are influencing the energy budget of the planet from which the climate is driven. All of the circulation of air and ocean water, all of cloud formation, precipitation formation, and its distribution are certainly driven by the energy budget of the planet. So you make an indirect inference there that the answer is yes. By how much will temperatures change over the next 100 years and where? That is a very fair question, and one that I don't think anyone in this room can answer with any real definition, but I'll show you a range of answers. a couple of detailed technical questions, and then a very, very interesting question which I'll get to at the end, that is, has science determined whether there is a safe level of concentration of greenhouse gas? At first I didn't understand where that question had come from, and then I realized that the 1992 treaty that the former President Bush had signed committed the nations of the world to preventing a dangerous accumulation. So this is a fair question. What is a safe level? So I'll now touch on our answers to those questions, and there may be some disagreement with our replies, but I at least want to mention them. First of all, about are humans causing the climate change that we're observing right now? This is just a different rendition of the temperatures I showed you earlier from the 20th century. I'll try that a little bit better. Where the blue marks indicate years when the global average temperature was below the average for this 120-year period, 2000 back to 1880. So it was cooler than the average of the entire period up until about 1930, and then basically warmer than average since. But once again, there's evidence of a warming that took place up until about the year 1940, then a slight cooling until the late 70s or 1980, and then a rapid warming. Well, what can we say about this? There is a rather good theory, but which will be extremely difficult to prove, as to why there was a slight cooling from 1940 to 1975 or so. Those were the years when the emissions of sulfur during coal burning were the largest in the world. Since then, sulfur emissions from coal have been contained much better. Not that it will always be contained, but the amount of sulfur in the air is less. The amount of sulfate aerosol, which reflects sunlight back to space, is less. So given that the sulfur was increasing during that time, it might have been enough to cause a cooling, especially in the industrially polluted regions of the northern hemisphere. And in fact, that's what the data shows. The cooling was most pronounced in downwind areas from those places where coal burning was maximizing during 1940 to 1975. Probably the most important part of this graph, though, is the last 20 years. Because I said earlier that one of the theories for all of the climate change of the last couple hundred years is natural variability caused by changes in the sun. So one idea has been that the sun in its cycles and its long-term geological scale stellar evolution might be getting warmer and emitting more visible light. Well, what's interesting about this last 20 years is that not only is that the period of the most rapid temperature rise in all of our observations, and the highest temperatures of all, and that this rate of variability is larger than anyone can explain with known natural causes. Our best computer models today are unable to generate that kind of variance even when things like large El Nino cycles are imposed arbitrarily in the models to try to generate this kind of rapid change. So the remaining good idea was that perhaps there had been some burst of activity from the sun. Well, what's special about this last 20 years is it's also the first time in human history that humans have been able to measure the output of the sun with enough stability and precision to answer that question. This curve is from Judith Lean, who's at the Naval Research Lab. And what Judith has done, besides building her own instruments and flying them on satellites, is to interpret data from other satellites. And she's strung together here data from 3 satellites, which is always difficult. But I believe she's matched the data as well as can be matched, showing again the 1,368 watts per square meter incident on the Earth at the top of the atmosphere. In fact, a couple of watts down from that, showing the output of the sun varying with the kind of 11-year cycle that we've all heard about, and returning to where it started 20 years before, if in fact just slightly below. So anyone who wants to theorize now that the warming of the last 20 years is caused by excess output from the sun has a very difficult time. It's why the weight of opinion has changed in the last few years. the weight of the evidence and the weight of opinion has changed towards believing that we are beginning to see a climate signal, namely a warming, caused by human activities. I'll talk about two more questions before I stop. Has science determined whether there is a safe level of concentration of greenhouse gases? And the answer is probably no, but it's more complicated, because some climate change will end up being beneficial to some people. Some climate change will turn out to be detrimental, but it will be disruptive in some way. The rate of disruption and the size of the disruption then is going to be key. How quickly can humans respond? How quickly can other animals or vegetation respond? Will depend on the size of the climate change and its rapidity. So if we focus on human installations for a moment, you can then see that there will be different answers to this question of whether or not there is a safe level of concentration of greenhouse gases, depending on the rate of accumulation, the rate at which the climate responds and exactly how, and then also on the nature of the people. How much money do they have? How much technical know-how do they have? How much infrastructure and knowledge do they have? I will say a word about changes in the next 100 years. This graph is messy, and that's the very meaning of it that I want to convey. This is an estimate of global average temperature increase in the coming 100 years as a function of scenario. And the details are not important. But what you might call a business as usual progression, where we simply use the same energy sources we've been using with moderate population growth, might lead to a global average temperature increase of maybe 3 degrees centigrade or 5 degrees Fahrenheit in the next 100 years. But there's so many assumptions built in, some of them physical modeling, some of them human behavior. On the high side of the graph, we can get up to 5 or 6 degrees centigrade warming if population grows more quickly, if we continue to use fossil fuels in the same fraction we are now, and if the climate sensitivities go in that direction. If, on the other hand, our human population numbers are more limited, we use energy less and transition to non-fossil fuel energies, and the climate sensitivities are less than our models calculate now, we could end up with a warming by the end of the next century only about twice or 3 times as big as we've seen in the last 20 years. But it will be warmer. And it will be warmer because there is inertia built into the system. The beautiful ocean observations made in the last 40 or 50 years that show how much heat has been absorbed by the world's oceans, and Walter Monk published a paper just a month ago showing that we still cannot understand all the changes in sea level, even though that new heat absorption, presumably greenhouse heat, is well quantified. There are a lot of surprises still built into the system, even in average temperatures. I'll show just another graph or two of some other likely changes, because climate is far more than temperatures. In fact, we don't get very fearful when we talk about average temperatures. We have to think much more seriously about temperature extremes. It's the temperature extremes that derive our need for electricity, for water, and for biological impacts on humans and other species. So this is just a table, in fact, taken from one of the IPCC reports of likely and unlikely phenomena that will occur in the next 100 years or so. With the left-hand column representing the confidence in the prediction, and I'll read just a couple. Changes in phenomenon. Higher maximum temperatures and more hot days over nearly all land areas. This is projected to be very likely. It's likely because the physics of the situation suggests it. As you go farther away from oceans and away from the heat capacity of the water, more towards the continental interiors, the extremes of the solar heating in the daytime and the cooling at night lead to dynamics that simply work this way. We will expect higher maximum temperatures and more hot days over nearly all land areas, and our computer models, the detailed three-dimensional models, are also predicting this. So in our grain belts, in the north Middle West U.S., southern Canada, the Asian continent, the former Soviet Union, we still have questions with these higher maximum temperatures. What will happen with rainfalls, and what will happen with the nighttime minimum temperatures? So how much will the growing season be extended? I'll just mention one or two others. One of the most interesting and difficult predictions to make is summer continental drying and risk of drought. This is still not very well predicted. There will continue to be natural droughts on top of it all, so it's very difficult, and it will be difficult for us to make reliable predictions and then to test them against actual observations. Precipitation is probably the most difficult variable of all to predict, and unfortunately one of the most important, because exactly what happens with climate as temperatures rise, it will be very important to know what happens with our precipitation patterns as a function of those increasing temperatures. So this chart is just meant to give a flavor of some of the other climate variables, where in this case the White House questions were focused on those variables, but we cannot do a very good job of predicting. Just as a reminder, though, we really must keep track of many climate variables, not just temperatures, not just average temperatures and the minimum and maximum temperatures, but also wind patterns, ocean currents, sea level, and sea ice patterns, in which we're seeing some dramatic changes right now, probably due more to natural variability in the Arctic right now as compared to what might be driven by the enhanced greenhouse effect. Precipitation, types, amounts, frequencies, and seasonality, soil moisture amount, and so forth. Many other variables of climate. There are feedbacks built in here that are also important that the climate models are trying to predict now. For example, soil moisture. If you've ever been in the Midwestern U.S. at the time that snowmelt occurs, you suddenly go from a surface which is white and reflective with the snow melts, and suddenly there's black, wet soil. The climate feedback there is quite strong. All of a sudden the sunlight is absorbed, the soil becomes warmer, the evaporation rate increases, so that if we have an earlier snowmelt, earlier in the season, the soils will become warmer and hence drier earlier in the season, so that this is what the kind of feedback that gives rise to concerns over later summer droughts. On the other hand, quantifying these feedbacks in mathematical models is very difficult. I just have a quick slide to show, to illustrate one source of uncertainty in trying to predict what climate changes will occur in the next 100 years. Our mathematical models now that try to simulate the climate, both natural and human influenced, are written such that there are grid squares that you can barely see in this slide. This is a grid square showing how climate models were about 20 years ago, with essentially 2 or 3 degrees or 5 degrees of latitude and longitude on a side. This grid square is better, obviously, a finer mesh grid that looks more like today's climate models, and eventually mathematical models embodied in computers that will have such a small mesh that we will begin to get, we hope, reliable predictions on a smaller scale that will be more meaningful. But there are many other sources of uncertainty in climate model predictions now, some of which depend on human activities. So that in trying to answer these questions, what will be the consequences of global warming, whether or not the climate changes will be safe or not, by exactly how much will temperatures change over the next 100 years and where, we have to admit that there are at least 2 kinds of uncertainty. The physical and biological processes that we are trying to model with mathematical models, but then human behavior also. This is obviously a very rough graph of human population numbers, because a real graph would show fluctuations, for example, during times of famine and disease and wars, so that the actual graph is not this smooth, but this is not a very inaccurate graph either. Human numbers have increased from a couple of 100 million 2,000 years ago to where we stand now at about 6.3 billion. And when you graph the numbers like this, it looks quite dramatic. Now, in fact, there is some reason to hope, because human population growth rates have decreased in the last 20 to 30 years. The percentage growth rates have decreased quite a bit. The actual growth rate in human numbers has peaked at about 90 million per year. It's now closer to 70 million per year, so the actual growth rate itself has slowed down, so that there's some hope that human population numbers will level off at 9 billion, or perhaps even a little less than 9 billion in the next 50 years. But there's still a lot of momentum built into the system, and a human population number of less than 9 billion people total is not that likely. But people who think that the human impact on the environment and climate change is simply controlled by population are not totally right either. And you can see this by trying to just factor where carbon dioxide emissions come from. In this graph, or in this chart, I have a little equation which says that CO2 emissions, for example, per year, equal the multiplication of three factors. One is the emissions of carbon dioxide per unit produced. Well, what is a unit? A unit might be an automobile, or a pane of glass, or a pair of shoes, or something that humans are using, multiplied by the number of units consumed per person. So this first factor, if you will, is technological efficiency. And you can begin to see that there are technological ways to limit this carbon dioxide emissions per unit produced. For example, if there were a fuel source that didn't emit any carbon dioxide at all, this number could be 0, but we're a long way from there. The second factor is lifestyle. Affluence, standard of living, consumption if you prefer, the number of shoes per person, the number of panes of glass per person, or the number of automobiles per person. And then the final factor is population. I like to look at the situation like this because it shows us simultaneously the difficulty of predicting the future, but also how much human behavior is involved in the future. How much we can change the future by our behavior, by our numbers, by our lifestyle, and by our technology. I'll stop here and simply say that this was a wonderful experience, and I also want to thank everybody for the opportunity to present the James R. Arnold Lecture, the first one, and hope that there are many, many more, better than this one, with larger crowds of old friends, and drawing more young people in too. So thank you again.